Hey Royals, in today's lesson we're going to look at a concept known as power. So far in this unit we've talked about energy transformations, we've talked about conservation of energy, and we've also talked about different forms of energy. But we really haven't thought about or even investigated how quickly can energy change from one form to another. And when we start talking about that concept, we are actually discussing power. So power can be defined as the rate of change or how quickly energy changes from one form to another. All right, so if we're looking at this situation, we have an equation for it. We define power as the work divided by change in time or change in energy with respect to time. So the example that's given to us on our page is that imagine you're trying to pass a transport truck on a highway, and it's really important to us to know how quickly can I change that chemical energy in my gasoline of my car into kinetic energy so that I can actually make that pass around that transport truck. All right, so the units for power are measured in joules per second, or more often referred to as the watt. So if you think about the electric light bulb in your house, you often see 60-watt light bulbs or 100-watt light bulbs. It's just a reference of how much energy they use per second. So often you might also see a unit called horsepower for discussing power. And a horsepower is an English unit which, weirdly enough, is referred to as in terms of horses, and it does relate back to horses. But for us, we're going to assume that one horsepower is equivalent to 746 joules per second or 746 watts. Okay, so I'm going to ask you a question. I'm going to then pause the video and I want you to think about the question I'm about to pose. So a 100 kilogram weightlifter is going to lift up a 190 kilogram mass above their head. I also have a 50 kilogram sprinter, and they're going to race off the starting line of a race, and I want to know which of these two people exerts more power. The weightlifter is going to be just a simple quick lift above their head, and then the sprinter is going to take 3 seconds to accelerate. So I'm going to pause the video. I want you to think about which of these two athletes exerts more power. So you may have written down one of these two athletes as being more powerful or exerting more power. So we're going to actually investigate this by numerically calculating how much power each of these athletes outputs. So for the weightlifter, we're told that their mass, and I'll just put MW for the weightlifter, is 100 kilograms. And then they're going to lift a barbell, so I'll call MB for the barbell, is 190 kilograms. That's what they're going to actually lift. And they're going to lift it to a height of 1.9 meters above the ground. And it's going to take them 1.8 seconds to do so. Okay, so I want to calculate the power output of this athlete. So in order to do that, I need to determine the energy that is being transferred. So I'm going to say that the change in energy is going to be based off of a change in height. So this person is lifting a barbell up into the air. It's going to be a change in height, so I'm going to calculate the change in gravitational potential energy. So that will be mg delta h. So what is the m in this case? What's actually changing height? It's not this weightlifter, it's the barbell. So I'm going to use the 190 kilograms to represent that's the mass that is changing. All right, so it's multiplied by 9.8 meters per second squared, and I multiply it by the change in height. Well, I'm assuming that the barbell starts on the ground, and it's lifted to a height of 1.9 meters. So I'm going to multiply it by 1.9 meters. And that gives me an energy of 3,537.8 joules of energy. So that tells me the change in energy that occurs when I lift this barbell up into the air, which means I can calculate the power output as the change in energy, in this case gravitational, with respect to change in time. So that tells me it's 3,537.8 joules divided by the time of 1.8 seconds. And when we do that, we get an answer of 1,965.444 blah, blah, blah watts. So that tells me that the weightlifter outputs a power of nearly 2,000 watts. When you think about the light bulb, that's 100 watts. That's pretty impressive. Now, let's think about that sprinter. The sprinter, their mass is 50 kilograms. Their initial speed is 0 meters a second, and their final speed is, we're going to say, 11 meters a second. And they're doing this in 3 seconds. Okay, so in this case, the change in energy is not gravitational potential energy. However, it's kinetic energy because I'm changing speeds. So I'm going to say that my change in energy is kinetic, and that means that it's the final kinetic energy, mv2 squared, minus the initial 1/2 mv1 squared. And I'm going to substitute my values. 1/2 of the mass, 50 kilograms. Final velocity or final speed is 11 meters a second. And I need to square that, not the seconds, but the whole term needs to be squared. Minus 1/2 of the mass of 50 kilograms multiplied by 0 meters a second, and we square that. So working through this piece here, the second term, because it's multiplied by 0, it's going to essentially be 0, which tells me that the change in kinetic energy is equal to 3,025 joules. So we now know the change in energy. We can actually calculate the power output of this sprinter. So it's going to be the change in kinetic energy in this case, divided by the change in time, which is 3,025 joules in 3 seconds, which tells me that my power output of this sprinter is 1,008.333 blah, blah, blah. It continues on watts. And there is my power output for my sprinter. So when you look at this, you might think the weightlifter is more powerful than our sprinter. However, that was a loaded question. Which of the two athletes is more powerful? Because the weightlifter has more mass than our sprinter. So realistically, we shouldn't be comparing output powers. We should be comparing what's known as specific power. And specific power is based off of how much power an individual or an object can output versus how heavy it is. So you would think that a heavier object, if it outputs the same amount of power, should be less powerful, right? So let's compare the two athletes, but in this case, based off of their masses. Okay, and we'll do that based on, and we'll call it specific power. So I'm just going to draw a line down the middle of my page here. And I'm going to say the weightlifter, and we'll call this one the sprinter. Okay, so the weightlifter's specific power is going to be their power per mass. Right, so the specific power, in this case, my weightlifter had a power output of a 1,965 watts, and they had a mass of 100 kilograms, which if you work this through, it gives you 19.65 watts per kilogram, or that's about 20 watts per kilogram. Now the sprinter, same idea. Sprinter's specific power is their power per mass. Their power output was 1,008.4 watts. And I divide that by their mass of 50 kilograms. And we find out that it's just over 20, so 20.166 watts per kilogram, which is roughly just 20 watts per kilogram. So you can see that both these athletes were equally powerful. They had the same specific power based off of their output power relative to their mass. So it should be pointed out that most humans, the peak output power that we can sustain for short bursts of time is about 20 watts per kilogram. So both these athletes are demonstrating that. But when you look at elite athletes, although I'm talking about elite cyclists, swimmers, marathon runners, the ones who train constantly, like the ones that you might see at the Olympics or the NHL playoffs or the MLB playoffs or something, elite athletes, their specific power is about 5 watts per kilogram. And that can be sustained for long periods of time versus our short bursts, like a football lineman can output about 20 watts per kilogram. Okay, so in this lesson, we looked at power as a change in energy with respect to time, or work with respect to time. We also looked at a term called specific power. And I'm going to ask you, if you have any questions or concerns, please reach out to me, let me know, and I'll do my best to help you out.